Welcome to the Ricci Flow Nutrition Podcast. My name is Cameron Borg. On this episode, I had the pleasure of speaking with Michael Holick. Michael is an American endocrinologist and world's leading expert on vitamin D. He is known for his discovery of the active form of vitamin D and the development of the assay for the circulating form, one of the most ordered assays ever. Michael has specialised in conditions including psoriasis, osteomalacia, and hypermobility syndromes. He is the author of several popular books including The Vitamin D Solution and The UV Advantage. Michael's work has had a huge impact on medicine, and he has been the recipient of many awards including the Linus Pauling Prize in Human Nutrition, the Robert H. Herman Award from the American Society of Clinical Nutrition, and NIH's General Clinical Research Center's Program Award for Excellence in Clinical Research. It was a huge honor to get to speak with Michael. His contributions to medicine have been enormous, and he has battled myopic and biased dermatologists essentially because his work brings a broader context to the conversation of health and sun exposure, a topic that has become very controversial due to the doubling down of both professionals and institutions on the idea that sunlight is harmful, which is undeniably false. Michael continues to preach the message of sensible sun exposure, as well as working with patients and researching to further understand the role of vitamin D and its related compounds in human health. With all this being said, I hope you enjoy the episode. All right, Michael, I've been waiting for quite some time to get the opportunity to speak with you. I've been a bit of a fan of your work for several years, so thank you so much for giving me some of your time.
My pleasure.
I'd like to know how you basically got involved in vitamin D in the first place. I believe you basically discovered the circulating form of vitamin D, which is quite an enormous thing, particularly in the world today. Vitamin D is very important. So how did you get involved in all of this?
So, everybody probably thinks that, I was very thoughtful in this whole process. And I recount this story to students all the time. Because what a student wants to do when they're in graduate school is to work with a mentor that is investigating the hottest topic at the time. And the hottest topic at that time was that DNA had just been discovered and that a lot of work was now going to be done in understanding how DNA works. And I was keen to be involved. And so I went to several professors and, they informed me that they had a lot of experienced postdoctoral fellows and lots of graduate students, and they really didn't need a new graduate student. And so they informed me that I should go over and see Dr. DeLuca, who's working in vitamin D. And I said, I have no interest in working in vitamin D. And they said, it doesn't matter what your interest is. You got to talk to him because that's likely what you're going to be doing for your PhD or your PhD research. So I went over and visited with him. And it turns out that I had originally been accepted into the medical microbiology program at the University of Wisconsin. And for my first year at the University of Wisconsin, I was a teaching assistant and was teaching about medical microbiology. And I wanted to now get involved in DNA research in microbes and in bacteria. And my professors at the time had no interest in that. They were interested in looking at antibiotics and how they, kill bacteria, right, to see which antibiotic is the best. So I told them, thank you very much, but I'm going to go over to the Department of Biochemistry. And so when I arrived at the biochemistry department, I told them that I've been accepted to the graduate program at the University of Wisconsin. And therefore, you should accept me into the biochemistry department. And they did. And it turns out that I show up 1 year after all the other students had started. And when I was accepted into the program, I was told, well, now you have to take your prelim to decide on whether or not you're able to go forward and maybe, get your PhD degree. And so I explained that I had not had any biochemistry. And all the students had biochemistry for a year. I was a chemist. I had an interest in biochemistry, and I had done research in biochemistry, but I had really no formal education in biochemistry. So the outcome was clear after I took my prelim exam, which was I basically failed. So Dr. DeLuca calls me into his office and he says, Michael, biochemistry is going to be too difficult for you. And that what you should do is go into pharmacology or physiology. And I said, I want to be a biochemist. And he said, look, I don't want to discourage you, but you're not going to be able to get your PhD right now. You're going to have to go and get a master's degree first. And it's going to take you 2 to 3 years. And then if you're lucky and you now pass in front of the biochemistry board, then maybe they'll permit you to get your PhD. And to do that is going to take another 3 to 5 years. So I don't want to discourage you, but it's going to take you probably minimum 5 up to 7 to 8 years for you to get your PhD. So I encourage you, go to the pharmacology and physiology departments and get your PhD there. And I said, no, I want to be a biochemist. Okay. So I arrive in the summer of 1979. And all of a sudden, we had known already because Dr. DeLuca's group had done this. They had given pigs huge doses of vitamin D, and they had identified 25 hydroxy vitamin D in the blood. But the problem was that they were giving massive doses, and how do you know how important it is for humans? And so as a result, he gets a phone call in July of 1979 saying from Dr. Avioli in St. Louis that he's been collecting blood from patients with a rare calcium metabolism disorder known as hypoparathyroidism, and that these patients were getting very high doses of vitamin D. And he had been collecting their blood. And he said, would you be interested in this blood? And that maybe one of your students could identify what was in the human blood. So Dr. DeLuca said, okay, everybody else had projects in the lab and I didn't. So he gave me the blood, 100 milliliters of human blood. And he said, Holick, follow the exact procedure for the pig blood, and that maybe in a year, you can then get your master's degree. Well, I was very gung-ho, and I don't sleep very much. I was sleeping like 3-4 hours a night. So I would work a good 14 hours a day. So I immediately started in August of 1979 and continued daily. And I came up on Thanksgiving morning with the realization the night before that I had evaluated all separation techniques known at the time, and that it looked like I failed because there was a contaminant in human blood that was not in pig blood. Well, it turns out that on Thanksgiving morning, I walked into the laboratory, and I was the low man on the totem pole, so I actually sat right by the door. So I had no laboratory desk myself. And I walk in and I look up on the shelf and I see a bottle that says Cefidex LH20. Now, I remembered from my undergraduate work when I was working with a fungus and isolating an enzyme that Cefidex separates things based on size. So I decided, what the heck, maybe this could work. So I took the material off the shelf and I mixed it with chloroform and hexane. I put on my sample, and 4 hours later, I had identified the major circulating form of vitamin D and received my master's degree.
Wow.
So I completed my master's degree in 3 months. And then the hunt was on, because we knew that 25 hydroxy vitamin D produced in the liver, when you gave it to rats that were vitamin D deficient, it took about 12 hours to work. For vitamin D, it took about 24 hours to work. And the question was, is the 25-hydroxy vitamin D being activated? And so the hunt was on. There were 3 laboratories, one in Cambridge by Kodachek's group, one in California by Tony Norman's group, and the DeLuca group. And initially, the thinking was, look, we took pigs, we gave them massive amounts of vitamin D, and so why don't we do the same thing and isolate the intestine? Because it was thought that the vitamin D works in the intestine, so it made sense that the active form would be made in the intestine. Makes sense. And so a postdoc got the job, and I was just the kind of underling graduate student. And so I started to say in early 19, so it was 69, not 79. And then in early 1970, I went to DeLuca and I said, look, this doesn't make any sense to me, that to give massive amounts and thinking that the body's going to make active material from that makes no sense. So I suggested that the only way to get this done is to grow. I calculated from everything and the information I had, I needed 1,500 vitamin D deficient chickens, and that they needed to get a physiologic dose of radioactive vitamin D3. And I figured that I would be able to get 10 micrograms from that source. And so at the time, they thought that was nuts, but they said, why don't you go ahead? And so I started growing chickens in the summer of 1970, and 500 chickens at a time. So 6 weeks, I had 500 chickens. My good friend, Jack Umdahl, he was a postdoc. We sacrificed them, took the intestine out, and collected them. And then 6 weeks later, I got another 500. And then on BBC, there's a news report. Major discovery in vitamin D by the Kodachek group in Cambridge, England. Well, Dr. DeLuca was apoplectic. He thought that was it. We'd lost the game. And so he comes to me the next morning and says to me, I want you to start your study right now. And why and how I would do this as a graduate student, but I told him no. And I explained to him I needed 1,500. That's what I calculated. I needed 1,500. Well, he got obviously angry with me, and he told me, who are you? I mean, I am your mentor. I am telling you what to do. And so I then said, you're right. I mean, what could I do? So I said, okay, tomorrow morning I will come in and I will begin with the 1,000 intestines. So I come in the next morning, I start to thaw the intestines that I have, and he comes to me and he says, Holick, you've been right all along, right? And you're probably right again. And so we'll wait for the 1,500 intestines. So I waited 6 more weeks. And then I started the process of these chromatography, separating all of it. On Christmas Eve, I flew home. I wished my parents a Merry Christmas. I flew back the next day because I told them that we are in a race to be the first to identify the active form of vitamin D. And so I got back, and as I was continuing my work of trying to separate all the junk from it, we now heard what was the discovery in Kodachek's group, which was, again, it was assumed that when you gave radioactive vitamin D and it went to the liver to get converted to 25-hydroxy D, and then it showed up in the intestine. So the thinking was that the intestine was activating. But a student in Kodachek's group, what they did, which made good sense, And we had done it as well. Why not just take an intestine and add 25-hydroxy-D, incubate it, and get the active form? And you can get as much as you want. And we did that with rats, with chicken, and it didn't work.
Mm.
What the group did in Cambridge, they took the intestine and the bone and the heart and the brain and the kidneys, and they found it was the kidneys, the kidneys activated vitamin D. So now I knew I was in trouble, because that means that the Kotichek group had a very simple way of making lots of this. And I didn't. I had this tiny, tiny amount. And so about the first week of January, I realized that I had come to the end of the rope, and that I had exhausted. I had developed an additional separation techniques. I had done 17 different chromatography techniques, and we still had like 500 micrograms of junk with my 8 micrograms of material that I wanted. And so the thinking was that was it. We're finished. And then I thought about this, and I said, look, we kind of know part of the structure, because we know vitamin D has a 3-hydroxyl group. We know that it has a 25-hydroxyl group. And we were thinking, and from Kotichek's work, that it's likely to be somewhere in the A ring at the 1 position. And so I said, look, that would mean that you have 2 secondary hydroxyl groups and a tertiary hydroxyl group. So why not completely what we call silate all the hydroxyl groups, and then selectively remove the 2 secondary and keep the tertiary. And by doing so, you would change its chromatography properties. And ultimately, after a couple of times of failing, I finally succeeded. It worked. And as a result, we went down with Dr. Heinrich Snow's, put it in the mass spectrometer, and there it was. We knew the structure for the active form of vitamin D. And we immediately published, and we beat out the Cambridge group by 2 weeks. So if I had gone home for Christmas for a whole nice vacation for a couple of weeks, we definitely would have been beaten. So that was my introduction to vitamin D. And I got my master's degree. I completed my master's degree in 3 months and my PhD in 1 year. So in 1971. And I wanted to always be a physician scientist. And so I then became a postdoc full-time, and then I applied to medical school at University of Wisconsin. So I was a full-time postdoc and a full-time medical student at the University of Wisconsin, and published, like, I think it was 42 major publications in a period of 5 years.
Wow.
And then I became fascinated with vitamin D, because I wanted to know, why is vitamin D called the sunshine vitamin? I mean, we knew, of course, that when you're exposed to sunlight, you make vitamin D. And I wanted to know why. And I wanted to know time of day, season, latitude, degree of skin pigmentation, sunscreen. How does it influence vitamin D production? So for a decade after I had left the DeLuca lab, I went off to Mass General Hospital and became a resident for 2 years. And I set up my photobiology lab at the same time. So I was basically a full-time scientist and a full-time resident. And I started all of those photobiology studies. And then I began to realize in the 1980s that your skin not only makes vitamin D from sun exposure, but that it has a vitamin D receptor. Now, why would a vitamin D receptor, right, the active form of vitamin D, be in your skin? I wanted to know why. So grew up skin cells, keratinocytes, and added the active form of vitamin D. And by the way, while I was in medical school, my roommate and I were the first to chemically make the active form of vitamin D. 21-step synthesis took 2 years. And the stuff that I made in a test tube was given to children with rare rickets that were wheelchair bound and started walking again, and to kidney failure patients who had severe bone disease. They again had helped them substantially. And to this day, the active form of vitamin D that I discovered is used worldwide in tens of millions of people with kidney disease. So now, why is your skin recognizing active vitamin D? And I found that it inhibited the growth and it caused these cells to mature. So I put my MD hat back on and I asked the question, is there some practical application? And it turns out that there's a skin disorder called psoriasis, right? About 3 to 5% of the world's population. And so I decided that I was going to do a clinical trial. Now, I am now at Tufts Medical School, and I've been recruited there. I'm a professor now of medicine, and I'm in the USDA, United States Department of Agriculture building for the aged. And I am now conducting research. And nobody had ever taught us in medical school how do you formulate medications to treat. And so I decided that the material that I chemically synthesized, I decided to put in Vaseline. Well, how do you do that? So I figured, what the heck? So I warmed up Vaseline on a hot plate to make it liquid. I added my active vitamin D. I then called up the FDA and said that I want to do a clinical trial. And they said, well, do you know if it's toxic in rats? And I said, no. So they said, well, why don't you get some rats, topically apply it, and see what happens? So I did. And I called them back and I said, they're perfectly fine. And so as a result, they said, they gave me an IND and I started my clinical trial. And so we had people with psoriasis that got on one arm Vaseline and the other arm Vaseline with the active vitamin D. And lo and behold, it worked. So I had introduced a whole new concept for the treatment of psoriasis back in early to mid 1980s, right? And again, I remained fascinated about vitamin D. We began to realize, working with Gary Schwartz down in South Carolina, that prostate cells and prostate cancer cells had a vitamin D receptor. And others were making the same observation, that cancer cells had this receptor. And so we added active vitamin D, and it inhibited cancer cell growth. And as you're aware now, that there is good data to show that improving your vitamin D status reduces your risk for deadly cancers, breast cancer, colon cancer, for example. I'm also was very interested to know how much vitamin D do you need? And if you take more vitamin D, does it have more health benefit? Right? The argument was that you only needed back around 1998, before 1998, it was thought you only needed 200 units of vitamin D. And then I was on the Institute of Medicine committee back in 1997, 98, and then we had recommended that it should be increased, and it was, but more studies needed to be done. And I started doing studies giving higher doses of vitamin D and showing that if you gave healthy adults 50,000 units once a week for 8 weeks, that you could have a decrease in their parathyroid hormone level by about, on average, 55%. So I concluded that unlike what was thought at the time, that vitamin D deficiency was a 25-hydroxy-D of less than 12 nanograms per ml, I convinced the world overnight that vitamin D deficiency has to be at least below 20. And so I published that in The Lancet, and basically it was accepted worldwide that vitamin D deficiency, less than 20 nanograms per ml. And then I started doing more studies, working with Ann DePape down at Merck, and we showed that if you look at blood levels of 25-hydroxy vitamin D in elderly women throughout the entire United States, that the PTH levels continue to come down until you're around 30 to 40 nanograms per ml. And so as a result, we began to realize that maybe your blood level needs to be above 20. And I was then asked by the Endocrine Society to chair a committee, and I brought in experts, pediatric and adult experts in vitamin D, and we reviewed the literature carefully. In the meantime, the Institute of Medicine had put together a separate panel, and they were beginning to deliberate as to what the definition should be. And they came out, said that vitamin D sufficiency is above 20 nanograms per ml. The Endocrine Society said, if you read the literature carefully, it actually should be at least 30 nanograms per ml. And this is based on the PTH levels plateauing at around 30 to 40 nanograms per ml. But more importantly, was a study by a German pathologist, Frimmel. In 2010, he published a paper where he had collected 675 samples of blood and bone from adults that died in an accident. And this is from ages 20 to 90 years of age. And he looked carefully at the bone, looking for evidence of vitamin D deficiency, osteomalacia. And he also related that to the blood level of 25-hydroxyvitamin D. And that group concluded that there's no evidence of seeing any vitamin D deficiency osteomalacia if you're at 30 nanograms per ml. And so based on that, also based on Dr. Heaney's work showing in other studies that maximum calcium absorption was at around 32 nanograms per ml, and that the PTH levels declined at around 30 nanograms per ml and began to plateau, the Endocrine Society said that vitamin D deficiency is less than 20, insufficiency is 21 to 29, and sufficiency is greater than 30, and up to 100 is perfectly safe. We also pointed out that the Institute of Medicine, in our opinion, got it wrong, because what they did was they took the number of individuals between 21 and 29 nanograms per ml and divided it by the individuals from 29 down to 0, and concluded that between 21 and 29, that less than 1% were vitamin D deficient based on osteomalacia. But they should never have done that. What they should have done, right, was to take the number, the numerator, how many, right, had osteomalacia versus how many didn't between 21 and 29. And when you do that, around 21% of healthy adults with blood levels between 21 and 29 nanograms per ml had evidence of osteomalacia. So with all that information put together and then made that recommendation.
I know here in Australia that we still use the old levels for deficiency and insufficiency, which is, in my opinion, completely insufficient in being able to determine people's status. I often see, I work in a hospital, and I often see people down at 50 millimoles per liter, which is 20 nanograms per milliliter.
Yep.
And there's nothing done about it whatsoever. And,
exactly.
And it's really difficult to convince them that the numbers, the ranges in the path labs, they have it wrong, because patients trust the numbers that are on the sheet of paper. It's very difficult to convince them otherwise, and to convince the doctors as well.
Yep. And what I do when I give my presentations, I tell the audience a couple of pieces of information that I think are really important to get an insight to where our blood level should be, which is, if we would be able to go back 10,000 years, right, and get blood samples from our hunter-gatherers, that would give us an insight, right? Mm-hmm. Well, a study was done where they took blood from Maasai herders and from Hasda Bushmen. And they showed that the blood levels are around 40 to 60 nanograms per ml. To get there, you would need to be on minimum 4,000 to 6,000 units of vitamin D a day. So that's about how much they were making on a daily basis. The other interesting observation that seems to be disparate, but really makes good sense, is that, as you know, human breast milk essentially contains no vitamin D. Now, that makes no sense from an evolutionary perspective, right? And so Bruce Hollis and Carol Wagner did a study, and they showed that if you give lactating women 6,400 units of vitamin D a day, they put enough vitamin D in their milk to satisfy their infant's requirement, right? And just like I said, the hunter-gatherers, their levels are at around 60 nanograms per ml. And you would have to be on about 5,000 to 6,000 units a day. And so, as a result, in my opinion, that's telling us where our blood level should be. And the Endocrine Society recommended that 40 to 60 nanograms is a great range to be in, and up to 100 is perfectly safe. So then we published a study. I'm sorry, go ahead.
Oh, I was going to say it's probably the best way to think about where we should be is to look back at our ancestral heritage. And obviously, the further north we went from the equator, the more depigmentation that had to evolve to allow more synthesis in the skin. So basically, even though we went further away, we were still maintaining optimal levels in that 40 to 60 sort of range, even though we were moving further away from the equator. And I was interested to see what you thought about the adaptations that came along with moving further away from the equator. Obviously, I spoke to Nina Jablonski, and she told me that depigmentation has evolved at least 3 times independently throughout our evolutionary history. So obviously, depigmentation is a big part of the story. Seafood consumption is also a big part of the story, because in those periods of time of the year where there is no UVB light, seafood was the only way you could really get an adequate amount of vitamin D through the diet. I was wondering were there any other sort of compensatory mechanisms that evolved to allow people at more northern latitudes to survive for that long period of time where there was no UVB light?
Right. So, well, one of them is, believe it or not, is that if you live at around 5,000 to 8,000 feet altitude, you actually do still make vitamin D probably in the wintertime.
And this is why the Sherpas are so dark.
Right. Yep. And so we did a study actually in India.
Wow.
I asked that question. And so because I developed a model where you could put an ampule out that contains 7-D hydrocholesterol, which is what converts in your skin to vitamin D. And we put it in Agra, which is at sea level. And then I gave it to a friend of mine that went to base camp in the Himalayas. And we could show very nicely in November, where you couldn't make any in Agra, that they were able to make a significant amount of vitamin D at 5,000, I guess it's probably meters, maybe. 5,000 meters. And so that's one of the adaptations. The second is, I'm pretty sure, and we're doing research right now to understand it, is that our hunter-gatherers were making vitamin D fat soluble, goes into your body fat. And then in the wintertime, they use that body fat as a source of energy. So they release the vitamin D. So I think as a result, they were able to compensate and have the ability to still be able to be vitamin D sufficient. And the half-life for 25-hydroxy-D, as you know, is 2 to 3 weeks.
Yeah, I believe dietary intake of vitamin D lasts a little bit less than the vitamin D you make on the skin from the sun, as far as how long it circulates, how long it's available for. Is that true?
That was our study. Yep, we did it.
Yeah.
And so we showed that when you ingest vitamin D, it rapidly goes up and it rapidly comes down within about 72 hours or so. But when you make it in your skin, right, you don't make vitamin D, right? So the 70 cholesterol converts to pre-D. Pre-D converts to vitamin D over a period of several hours. It's made in your keratinocytes, which is in a bloodless tissue, your epidermis, that now has to migrate, right, to the dermal capillary bed. And all of that takes time. And so as a result, we measured the blood levels of vitamin D for people taking it orally. And then we exposed them to a tanning bed and had them make vitamin D. And we could show that their blood level didn't go up as high, but it was sustained for a significant period of time. So that the
Interesting.
area under the curve was 2 to 3 times more than it was by taking it oral.
Something I found interesting to learn last year was this guy, Yakimov, showed that the top 50 microns of the skin can be photochemically bleached by the use of hydrogen peroxide and visible and UV light. And this top 50 microns is it photochemically bleaches the melanin layer, but it's also the place where there is the most lipids in the skin, this top 50 microns, which seems to suggest that our bodies are perfectly designed to accept and use the high energy photon that is UVB and UVA to do lots of things with sterols in the top layer of the skin. And that's why it's selectively bleaching the melanin in that very top layer, which is sort of counterproductive if you think melanin is there to protect the genetic material from the potential damage from those high energy photons. And it makes me wonder if there are other things that are being directly made aside from that interaction between 7-D hydroxycholesterol and a UVB photon. Are there other things that are being made directly in the skin with the increased lipid level in this top 50 microns?
Right. So a couple of thoughts. And if you go on the internet, you probably have seen it, is that they say that after you're exposed to sunlight, you should not bathe because you're going to wind up washing off the vitamin D on the surface of your skin. Not true. Most of your vitamin D, the pre-D, is made in the basal layer of your skin. So what is true is that your stratum corneum has a lot of lipid, right? And yes, the bleaching will remove a lot of the melanin. So it'll help the UV get to the basal layer to make pre-vitamin D.
Yeah.
Whether or not these other sterols up on top have any benefit is debatable because it's a bloodless tissue, right? And so unless you have good diffusion, right, probably not, right? That top layer is oily, is kind of almost like candlelight, right? Because it provides protection from water and from your environment, right? But I don't think that top layer, which is a dead layer, provides any biologic benefit other than protection.
Interesting. Do you think it has anything to do with scatter and allowing light to scatter and penetrate through in a way that is more beneficial to the synthesis of things like vitamin D?
Right. So it turns out that my very good friend who passed away, Don Crystal, became a multimillionaire because he realized something. And for the tanning industry, that he could develop a product that if you put it on your skin, it would enhance tanning. And that was all the rage. But what people didn't realize was that it is simply oil. And just like back in the 1950s when they were putting on cooking oil, right, women would go out on the beach. What you're doing is you're flattening the mirrors that are reflecting back the ultraviolet rays.
Yeah.
And as a result, more of them will penetrate. And as a result, you get more efficient production of melanin because you're being exposed to more UVA and UVB radiation.
Yeah, that's really fascinating. I know a lot of places who do red light therapy devices sell serums to put on your skin to allow the penetration of the light better. But it is interesting to note that that is changing the dynamics of the light that's coming in and interacting with your skin.
So I was just going to say, I've written about this as well because I'm really fascinated by it. which is that red light, blue light penetrate deep into your body, right? Because there's nothing there to absorb it. And that's why red laser therapy, right, has been very effective for wound healing and for a lot of other processes.
Yeah. Well, that's actually a good segue into me asking about the potential danger of exposure to narrowband blue light, particularly on a consistent basis. Most of our indoor lighting is narrowband blue, and blue, of course, is right next to violet and ultraviolet in the spectrum, and it is quite a high energy photon. And I know that it is capable of inducing reactive oxygen species, and it can be quite damaging, particularly when it's not balanced with the longer wavelengths, the reds and the near infrareds and so forth. What role do you think our artificial light environments might be playing in conditions like skin cancer, particularly basal cell carcinoma, which I think some commentators have suggested might be caused in some cases by exposure to artificial light rather than sunlight itself?
So, two thoughts about this. The first is that there is literature on blue light also having positive benefit to wound healing and the like. And I don't think, but I could be mistaken, that there's any good evidence that it has a negative consequence to the skin. But in terms of UVA, that is the culprit, in my opinion. And people don't take UVA seriously because UVB, of course, is all absorbed by DNA, RNA, and proteins in your epidermis. But UVA is not. And it's high energy. And it now goes into your dermis. It alters your immune system, right? We know that, right? It causes damage to your collagen matrix, increasing risk for wrinkling and damaging your skin. And then finally, in my opinion, because it causes a alteration in immune function, that it's ultimately responsible for the most deadly form of cancer, melanoma. And the reasoning that I have for this is the following. We know that when you're exposed to UVB or UVA, that you damage cells and that the immune system responds. But when you're exposed to UVA, it causes immune tolerance. So now, in my opinion, what's happening is that when you're exposed to UVA, you're causing immune tolerance. And now you develop a melanocyte that becomes altered in some way, cannot be recognized. And that as a result, melanoma occurs in the least sun-exposed areas because you have gazillion melanocytes, right, everywhere in your body, right? They all originated from your midbrain, right, from the neurocrest cells, right, which to me was incredibly fascinating, right? And as a result, once that cell becomes malignant, you don't really have the ability to fight it because you've already developed an immune tolerance to alterations in the melanocyte itself.
So that seems to me as though UVB and UVA have to work synergistically together to actually prevent any runaway shifts in the immune system that aren't adequately regulated.
Number one, absolutely. And then number two is UVB, right, is picked up by melanocytes at the dermal capillary bed, right? And they release melanosomes, right, up into the epidermis, covering the nuclei, right, just like an umbrella, helping to protect them. But if you're exposed to UVA, and this is why early on when I was an advisor for the tanning industry, I told them that this UVA is not good because when you're exposed to UVA, it penetrates deep. The melanocytes recognize this and they make melanosomes not to go into your epidermis to protect your skin, but down into the dermis. And therefore, even though you have darker skin, you're not protecting your epidermis, which is prone to developing non-melanoma skin cancer.
When you say UVA is bad, you mean specifically outside of the context of its natural exposure patterns.
Correct.
Right.
But also, well, yes and no. I mean, what's interesting to me is, right, the dermatologist would advise people, you go out and jog in the morning and late afternoon, right? Make your vitamin D and that less damaging to your skin. Turns out, in my opinion, it's the most damaging to your skin. You make no vitamin D, you're getting blasted by UVA radiation.
So clearly there is this period of time in the morning before the zenith angle gets sharp enough to allow UVB through. And likewise in the afternoon, we have these two periods sort of either side of the UVB period that are rich in UVA as well. I would think that nature had evolved to get that exposure, perhaps for some specific purpose, maybe to prepare for UVB and then after UVB, because we would have been outside for that whole cycle. So perhaps it's doing something that is important, but outside of the context of that whole day exposure, it can yield negative effects.
And we've done studies to show that UVB will stimulate the production of beta endorphin, which is why we think people feel better.
Mm-hmm.
UVA stimulates the release and production of nitric oxide, which causes vasodilation and decreases your blood pressure. So no, but UVA is not bad. It's just that you don't want to be blasted by it only in the morning.
Yeah.
Right.
Yeah.
You want to take advantage of the entire solar spectrum.
Yeah. And talking about beta endorphin, I want to ask you about POMC. Clearly, this is a very important genetic product that cleaves into all these different biogenic amines that are important for a variety of different things, not just tanning, also for things like arousal, like you said, endorphins. I believe there is literature suggesting that people with lower vitamin D have a greater risk of addictive behavior, probably through this endorphin pathway. We're designed to be sort of addicted to getting outside and getting in the sun. But these cleavage products, are they cleaved depending on the type of solar radiation we're exposed to? Like, are they cleaved based on certain wavelengths that we receive throughout the day?
It's a good question, but the cleavage, of course, is done by enzymes, right? It's the POMC, and it gives rise to ACTH, for example, right?
Yep.
And enkephalin, right? And beta endorphin.
Mm-hmm.
Now, whether or not UV plays any role in regulating the enzymes to do that, I don't think we know. But Dr. Slaminsky has spent a lot of effort showing that the POMC gene is definitely turned on, releasing ACTH, which we think will increase, therefore, cortisol, right? And help maybe reduce autoimmune disorders, for example.
Yeah, that's really fascinating. I've been following Slaminsky's work for quite a while, and some of his papers are really, really insightful. Is POMC predominantly the genetic expression of that gene and ultimately the production of the product? Is that predominantly generated through UV exposure on the skin or through the eyes or both?
Mainly through the skin.
Right.
I'm not aware of any data to show that you could stimulate pituitary ACTH production through the eyes.
Interesting.
Not that I'm aware of.
Okay.
Yeah, it's all produced in the skin. The POMC gene is turned on in the skin.
Right. And I remember speaking to Rebecca Mason a few years ago. She's in Sydney as well. And what's really interesting to me in the vitamin D research now is this increasing talk about these hydroxyderivatives, sort of these cousins of the vitamin D molecule that are made by a variety of different enzymes along the pathway. The one that has got the most attention at the moment, I think, is 20-hydroxyvitamin D, which is made by CYP11A1. And there are a bunch of different hydroxyderivatives that all seem to exert similar regulatory effects on cell cycles and apoptosis and whatnot. And I was wondering where you think this research is going. Obviously, vitamin D is not just the only thing that's going on here. What are these other hydroxyderivatives doing in the orchestra that is this regulation of cell cycles?
So, I know Rebecca very well and impressed with her work. And she actually had a very nice cancer model, right, that she had developed. And Andrei Slaminsky has been playing around with this now for quite a long time to show that the side chain can be removed as still hydroxylate. It has biologic function. But I've tried to get funding from NIH. And unfortunately, when study sections that have a dermatologist on it, they're not interested in funding anything related to beneficial effects of sunlight. So they shut my program down. I had been funded for well over 30 years, and I was not possible. Andre is now having a hard time getting funded. But there's a wealth of information in there, not only the metabolites, but also the photoproducts, the toxysterols, the supersterols. We did studies with them, and we showed that they had biologic action.
That's very interesting. It hits home particularly hard here in Australia, where the safe sun message is just completely out of whack. And in your book, you talk about this sort of trade-off. If we avoid sunlight, we think we're avoiding cancer, skin cancer, but what we're actually doing is increasing the risk of basically all of the other diseases: cardiovascular disease, diabetes, obesity. All of these other things go up completely disproportionately to the risk of non-melanoma skin cancer, which we know is increased by cumulative dose, whereas melanoma is a lot more complex, and that's the one obviously we're worried about. I think Prue Hart told me we don't even count non-melanoma skin cancer in our cancer statistics anymore because there's so many of them, and usually they get cut out and that's the end of them. So
exactly.
What would you say to someone who is avoiding sun because they think it's going to increase their risk of cancer? I want to know roughly what this trade-off really looks like.
Well, my recommendation has been the following. Most skin damage is from excessive exposure, which is your face, top of your hands, but not your arms, not your legs, not your back, certainly your neck. So I always recommend sun protection on face and top of your hands, right? Wear a nice broad rim hat, but certainly you can go out in a bathing suit for a short period of time for a sensible sun exposure. That's what I had recommended, right, in my book. And I worked with Ontometrics in California, and we developed that app, right? dminder.info, DIMINDER.info. It'll tell you in Australia, right? Or here in the United States, when you can make vitamin D, how much vitamin D you make, and it warns you for your skin type to get out and don't get a sunburn. So I always tell people, go out for about amount of time that's about 50% of the time that would cause a minimal erythemal dose, a light pinkness to your skin 24 hours later. There is, in my opinion, no evidence that even increases risk for non-melanoma skin cancer. But definitely has marked health benefits in all kinds of ways. Makes you feel better, improves your mood, makes vitamin D, makes beta endorphin, relaxes you, decreases your blood pressure, and the list goes on.
I think that I might be getting the exact number wrong, but in the book you talk about, I think it might have been from William B. Grant who did an ecological study, and basically he put forward the idea if people avoided the sun to decrease their risk of non-melanoma skin cancer, for every one person that was saved from a non-melanoma skin cancer, I think something like 400 people would develop a breast cancer or a prostate cancer or something like that. So it's just this completely horrible trade-off where if you're avoiding the sun, you may be reducing your risk of non-melanoma skin cancers, which typically don't kill people at all, but you are drastically increasing your risk of these deadly cancers, and particularly breast, prostate, and colon cancer are the ones that have the strongest evidence, I believe.
Agreed. And basically what the dermatology industry did and sunscreen industry did 50 years ago was simply to use the big C word, cancer, right? They never really explained that non-melanoma skin cancer is really pretty benign, easy to treat, easy to detect. But because they said it's the most common cancer, right? That's what got everybody's attention, and it got the legislators' attention, and then that was it. It was like a snowball that is still difficult to melt.
Yeah, well, I think it's quite telling that even IARC, I'm not sure when it was, but it was relatively recently, made a point on sunscreen that showed that it didn't really have any evidence to suggest that it was reducing those cancers. And in some cases, excess use of sunscreen would increase your risk because you're able to stay out much longer than you should, exposed to, like we said, these visible wavelengths that are as well doing damage. And the problem with the sunscreen industry is in order to block those dangerous visible wavelengths, the sunscreen has to be pigmented, which doesn't go down very well in the PC culture that we live in at the moment. I wanted to ask you about urocanic acid. This is something that Prue Hart has been working on, and obviously trying to figure out the non-vitamin D things that are happening with sun exposure that are regulating the immune system, because we do see, like the Garland brothers, for example, showing these beautiful relationships between distance from latitude and incidence of type 1 diabetes, for instance. And that doesn't seem to necessarily be related directly to vitamin D. There's obviously some other things going on as well. So what do you think about urocanic acid's role in this big picture with sunlight and health?
Yeah, don't have as much experience with urocanic acid, so I don't think I could really speak to it with any authority. So forgive me, but I'm going to have to pass on it.
That's okay. Yeah, there's a lot going on. It's just interesting to see that people are trying to find other things that are going on with sunlight other than vitamin
I'm familiar with it. I know it, but I don't really have a good sense of what its benefit is.
Okay, awesome. I think that's a pretty good place to wrap up. I mean, we've covered a lot of ground, and I want to be mindful of your time. Just to finish up, what are you working on now? Where are you headed with your work?
What I'm now interested in, because nobody else is interested in, which is great, is that vitamin D is fat soluble. We know that it gets into your body fat, which means it's getting into your live adipocytes. We are clueless as to what that mechanism is, and more importantly, what the mechanism is that will induce it to leave your adipocyte. So we're growing now fat cells, and we're playing around. We have a couple of different probes, fluorescent probes and radioactive probes, to try to understand that process.
That's really fascinating. I can't wait to read some more publications of yours when that comes out. I think it's a very important topic, particularly as I think somewhere around 50% of people are overweight or obese, not only in the States but in Australia as well. So hopefully you can find out a bit more about that. Thank you so much for your time. This has been a real honor.
Pleasure.
I've been waiting a long time to speak to you, so thank you.
Very kind of you. Nice pleasure to meet you.
Thank you so much for listening to this one. I really hope you enjoyed our conversation. I've left links to Michael's books and his app in the episode notes if you'd like to learn more. If you'd like to support the podcast, please subscribe, leave a positive review, as it really helps me reach more listeners and get more interesting guests on. If you'd like to keep up with my work, I've left links to all my social media platforms in the episode notes, so feel free to reach out. Thanks again for listening, everyone. Take care.